In this presentation, we'll review the 4 types of binary relations on A. Binary relations on a set A. So, from the very beginning, we introduced the binary relation A as being a subset of A cross A. The elements of the binary relation are ordered pairs. So when we say X, Y belongs to R, there's another notation, equivalent notation, X, R, Y. This is X related to Y. Let's take an example. A is a set 1, 2, and 3. And let's say the binary relation R is 1, 2, 1, 3, and 3, 3. There are essentially 2 possible ways to represent, main ways we use to represent this relation. One is a conceptual diagram, which is very useful in a lot of problems posing theoretical questions. So the set A consists of 1, 2, and 3. 1 related to 2, so we have an arrow from 1 to 2, 1 to 3, and 3 related to itself. Being related to itself translates into a loop from 3 to 3. So there's one way to represent this relation that we use frequently. Another way to represent this relation by using a matrix. This is because A has 3 elements, we use a matrix 3 by 3. The rows and the columns of the matrix are labeled with the elements of the set A. So this row corresponds to 1, row 2, row 3, column 1, column 2, column 3. So let's look at this would be a 0, 1 matrix. Element 1, which is in row 1, is related to 2 and 3, not related to itself. No loop, there is no loop from 1 to 1. So 0 here, but 1 related to 2 and 1 related to 3. Okay. Let's go to element 2. Element 2 there is no arrow emerging from 2, so 2 is not related to anything. So 0, 0, and 0. And finally, element 3 is only related to itself. So we put row 3, 0, 0, and 1, illustrating the fact that 3 is only related to itself. Okay, so let's get the 0, 1 matrix encoding the binary relation R, which we see above. So we either use the conceptual diagram for the relation, or depending on the context, we may use the matrix of the relation. Okay, so now let's discuss make an overview of the material discussed in class, the 4 basic types of relations. What does mean R reflexive? R reflexive means for every X, where X related to X. In terms of conceptual diagrams, reflexive means we will loop at any point. At every point. So other than that, we could have other, it doesn't really matter. So if we add or not add other connections, that does not change the fact that the relation is reflexive. So we can put 1 to 2 extra and 1 to 3. That's a reflexive relation because it has loops at any point. What does it mean, minimally reflexive? So minimally reflexive. That means only loops. So minimally reflexive, so reflexive and minimal with the property of being reflexive, let's assume would be equality. So equality the quality relation in which two elements are related only if they are, if and only if they are equal, is a relation which is visualized only with only loops at every point, a loop at every point, and nothing the rest. In terms of matrices, the matrix of a reflexive relation, every element is related to itself. So then doesn't really matter what is in rest. Right? That's how we recognize a reflexive relation by having ones on the diagonal. So speaking of this representation, we can make a quick count what's the number of reflexive relations on a set with n elements. Number of reflexive relations on A where the number of elements of A is 10. So we have to look at those matrices. That would be an n by n. So let's wait 3 by 3, but imagine we have n by n. On the diagonal with n elements in the diagonal, and off diagonal with n squared minus n elements not on the diagonal. So they are like the stars in this picture. So that with n squared minus n elements not on the diagonal. So therefore, with 2 to the power n squared minus n reflexive relations, because we can choose every element of diagonal can be either 0 or 1. We have two choices per element, and the choices are independent. So we get 2 to the power n squared minus n reflexive relation on A. Okay, so what was the total number of relations, number of binary relations on A? So there's another problem we discussed in class. Number of binary relations on A, where the number of elements of A is 10, because every such relation is a subset of A cross A, and A cross A has n squared elements. Being a Cartesian product, the number of elements in a Cartesian product is the product of the individual numbers of elements in the two vectors. So number of binary relations is 2 to the power n squared. So let's make a list of all binary relations on a set with 2 elements. So what's the number we expect? 2 to the power 2 squared. 2 squared is 4. So we want to see 16 binary relations. So let's see that. Okay, so let's assume the set with 2 elements is listed as 2 points. The top one, let's say it's 1, the bottom one is 2. The set A is 1, 2. 1 at the top, 2 at the bottom. So let's list first of all binary relations in which 1 and 2 are not connected. Therefore, the only possible choice is loops, if any. So no loops. Loop at 1, loop at 2, and loops at both 1 and 2. Okay, then among the points 1 and 2, we put the relation of one-way relation from 1 to 2. So otherwise, the situation of the loops remains the same. So 1 to 2, we have something like this. And the loops, the same structure of the loops, loop at 1 here, loop at 2 here, groups of both 1 and 2 here. And then these are all of them with a single arrow from 1 to 2, going from 1 in the direction of 2. Now, same for the arrow from 1 to 2 going backwards. So from 2 to 1. So an arrow like this, from 2 to 1. From 2 to 1, look at 1. From 2 to 1, sorry, from 2 to 1, no look, because the first. From 2 to 1, no look. From 2 to 1, look at 1. From 2 to 1, look at 2. And from 2 to 1, these two, the top is 1, the bottom is 2. From 2 to 1, and looks at both 1 and 2. And lastly, the elements 1 and 2 are related both ways. And then the same type of situation with the loops. So, related both ways. From 1 to 2 and 2 to 1, no loop. From 1 to 2, 2 to 1, loop at 1. From 1 to 2, 2 to 1, loop at 2. And finally, from 1 to 2, 2 to 1, and loops at both 1 and 2. Okay, so these are how many? So there are 16, which is 2 to the power 2 squared, 2 to the power n squared is the general formula for the total number of binary relations on a set with n elements. Okay, so how many of them are reflexive? Reflexive is 2 to the power n squared minus n, right, in general. So which is in this case 2 to the power 2 squared minus 2. So this will be to the power 2, right, which is 4, which are reflexive. So reflexive means loop at any point. So these are reflexive. Okay, let's move on. Symmetric relations. A binary relation subset of A cross A is symmetric if for every X and every Y, if X are Y, then Y are X. To understand this one, we have to understand that every relation between two different elements is two ways. So there is not only one way. So what would be a defeater? What does it mean? Sometimes it's good to know mathematical objects by negation, via negatives. So that means we have to imagine a structure that if you see it in the diagram, in the conceptual diagram, it is not symmetric. And if you don't see it, it's symmetric. So what is that pattern that if we see it is not symmetric? Basically, we cancel the symmetry, but if we don't see it, it's symmetric. So let's deny this. So that means symmetry means all two elements, all ways are two ways. So I want for a defeater to see an arrow going from one element to another, but not the one going back. So whenever you see such a pattern, that kind of annihilates the possibility of R being symmetric. So see this are not symmetric. Don't see this. R is symmetric. So knowledge by defeaters, like a negative knowledge. So, well, for example, this relation in this conceptual diagram, every relationship between two different elements is two ways. We don't see any defeater, which makes this relation symmetric. But this relation, for example, just a cycle 1 to 2, and we could have loops 2 to 3. This relation we see two defeaters here, so that's not symmetric because we see this defeater. So a simple side of this defeater will rule out R being symmetric. Okay, now a positive knowledge. A positive knowledge is if we work with matrices, how to recognize symmetric. The matrix of the relation is a symmetric matrix. So symmetric matrix corresponding to R. Okay, so symmetry means we don't even care what is on the diagonal, we have a single one, but whatever elements are reflected about the main diagonal are equal. So let's see, what will be the graph of this relation? So we have elements 1, 2, and 3. 1 raised to 2, 2 with 1, and with itself, and with 3, and 3 with 2. So that's the diagram corresponding to the binary relation with this matrix. So this being said, so let's try to use the concept of symmetric matrix. Every symmetric relation is a symmetric 0-1 matrix associated to it to count the total number of symmetric relations on a set with n elements. Number of symmetric relations on A with the number of elements of A is 10. Okay, so let's look at the matrix of the relation. Because of the symmetric character of the matrix, reflecting about the main diagonal produces equal elements. So we only need to provide values for the elements that are on the diagonal or above. So those elements stars. So if we know the values of those elements, zeros or ones, then we know the elements on the other side below diagonal. So if you know the values for the elements on the diagonal or above, we know everything because of the symmetry. So, for example, if we reflect about the diagonal, these two elements will be equal. So, reflecting about the diagonal produces equal elements. So it will be enough to know all the elements on or above diagonal. Let's see how many of them are here. So one way to put it is like we have n elements in the n stars in the first row, n minus 1 stars on the second row, n minus 2 stars on the on the third row, and so on. So the number of stars, total number of stars, be 1 plus 2 plus 3 plus n, which is 10 times n plus 1 over 2. And because every star can take a value of 0 or a 1, we have 2 to the power n times n plus 1 over 2 symmetric relations on A. Okay. Next, we'll go with antisymmetric. The R subset of A cross A is antisymmetric if for every x and every y, if x and y are pairwise related, so if x are y and y are x, then x equals to y. So in other words, related both ways implies equal. So a relation is antisymmetric whenever two related elements, whenever two elements are related both ways, it follows that they are equal. Let's see a defeater. What's a defeater for this relation? Then it's a pattern that if you notice it is not antisymmetric. If you don't notice it is antisymmetric. So defeater. So how to deny this? So antisymmetric means if related both ways, then equal. A denial of this would be see something which are related both ways yet not equal. Related both ways yet not equal. That's a defeater. That means, let's see it. There's a defeater for antisymmetry. And let me review that this was a defeater for symmetry. One-way road between two different points. Now let me use this conceptual knowledge of defeaters to produce an example of a relation which is both symmetric and antisymmetric, and secondly, a relation which is neither, not symmetric and not antisymmetric. Okay. Let's see something which is both symmetric and antisymmetric. What does it mean? We must not see any of those defeaters. So no pattern like this and no pattern like this. In other words, two different points cannot be joined in any way. So it cannot be joined one way, it cannot be joined two ways. So basically, this leaves us only one possibility, only loops, if any. So a symmetric and antisymmetric relation is a relation which only has loops, if any. If any, because empty relation is symmetric and antisymmetric, because we don't see any of those defeaters. So empty relation is symmetric and antisymmetric. So everything between empty relation and equality is is both symmetric and antisymmetric. As for the total number of relations which are both symmetric and antisymmetric, with n points in the set, this is the number of elements of A is n. For at every point with either a loop or nothing, so two choices per point, choices are independent, so with 2 to the power n primary relations on A which are both symmetric and antisymmetric. Okay, let's do another exercise which I did before. We also discussed about, again, another example involving the set A equals to 1, 2. Let's try to find okay, before this, if A equals to number of elements of A is 10, we have seen that 2 to the power n squared plus n, or n times n plus 1 over 2, symmetric relation of A. In particular, if the number of elements of A is 2, we have 2 to the power 2 times 3 divided by 2 is 8, symmetric relation of A. Let's use the ideas of defeaters to quickly sketch all the graphs of diagrams of those symmetric relations on the set 1, 2. Remember, no defeater for symmetry. So between the point 1 and point 2, either we have nothing or we have a two-way connection. So we have nothing and we have only loops. Nothing, no loop, loop at 1, loop at 2, loops at both 1 and 2. And then connected both ways and no loop, connected both ways, loop at 1, connected both ways, loop at 2, and connected both ways with loops at both 1 and 2. So we have 4 plus 4, 8, like we discussed before, symmetric relations on a set with 2 elements. Okay, we've seen the example of all relations which are symmetric and antisymmetric. They contain only loops. What about neither? Not symmetric and not antisymmetric. That means we have to draw pictures, diagrams, and we should show both defeaters. So a simple one would be defeater for symmetry, followed by a defeater for antisymmetry. So these relations are equals to 1, 2, 2, 3, 3, 2, subset of A cross A, where A is 1, 2, 3, 1, 2, 3. That relation is not symmetric or not antisymmetric. Okay. discuss transitive relations. Transitive relation means, so the best way to think about this, if I can get from CTA to CTB, and then if I can find some other transportation from CTB to CTC, then overall I can reach from CTA to CTC. So that's a connectivity relation, is like, as in I can reach from CTA to CTC by transiting through CTB. There's the idea here. So the formal definition for every X and every Y and every Z, 3 cities because we have a intermediate mode of transit. If X are Y and Y are Z, this implies X are Z. In terms of diagrams, that means if we see an arrow from X to Y, followed by an arrow from Y to Z, then we must see an arrow from X to Z. So must see an arrow from X to Z. Must see this. So there's the net effect. We're going from CTX to CTZ, transiting through CTY. Okay, so here's an example. A is, I don't know, 1, 2, 3, 4, 5, whatever, it doesn't really matter, give you any set of real numbers. So let's define the relation R subset of A cross A, in which X are Y if X less than or equal to Y. So let's see how what is the relation. So let's check. R is reflexive. Of course it is, because X is less than or equal to X. So that's a valid inequality for every X, right? Is it symmetric? So if X less than or equal to Y, this does not imply though that Y less than or equal to X. So that's not true. So the relation is not symmetric. Let's check R antisymmetric. That means if X less than or equal to Y and Y less than or equal to X, does it follow that X equals to Y? Of course it does. So if we have opposite inequalities of less than or equal type between two numbers, they must be equal. So far R is reflexive and antisymmetric. What about R transitive? For transitivity, let's check if X less than or equal to Y and Y less than or equal to Z, then it does follow that X less than or equal to Z will make this relation transitive. So the less than or equal relation is reflexive, antisymmetric, and transitive. Later on we discuss in depth partial order relations, which are defined just by being reflexive, antisymmetric, and transitive. And also, before them we'll discuss equivalence relations, which are reflexive, symmetric, and transitive.